Now if I will need the first derivative of the function at 1 and 1, which is positive 1. The first derivative of the function with respect to y at 1 and 1, which is negative 1. So all of this can be simplified to be h minus k. Now I can use the denominator, which is the remainder. It's going to be negative k h minus k over 1 plus k. And for the denominator, which is the root of h squared plus k squared. Now I can continue easily by, from this, to make the substitution. Instead of the denominator, we will have negative k of h minus k over 1 plus k divided by h squared plus k squared. Try to simplify stuff, moving 1 plus k to the denominator. So you will have 1 plus k times the root of h squared plus k squared times the negative k in h minus k. I want to point out at this time, or at this stage, all I want to do is to prove that this limit of existence is equal to 0. And it's very, very simple. Let's get an advantage from using the consequence of the squeeze theory, because this is a limit of a function in 2 dimensions. So I can separate this limit as I did by considering k over 1 plus k, and that's the limit of h and the k, times the limit of h and the k, okay, of course tends to 0, okay, to zeros, and this is for h minus k divided by the root of h squared plus k squared. This guy is equal to 1. All I have to, because, I'm sorry, this guy is equal to 0, because once k tends to 0, it's going to be 0 divided by 1, which is 0. So this part is equal to 0. For this one, or for this, the remaining of my problem, all I have to do is to check if the limit exists and is equal to 0 or it is equal to 1. So all I have to do is to continue for the check of this limit, which is really very simple, as you will see. So once more, okay, this is going to be the limit is equal to 0, and if you try to use this limit, it's going to be bound, because simply I can simply prove that h minus k divided by the root of h squared plus k squared is less than or equal h plus k divided by the root of h squared plus k squared, which is less than or equal, okay, to h squared plus k squared under square root plus the root of h squared plus k squared divided by h squared plus k squared. So as you can see, I will have 2 root of h squared plus k squared divided by the root of h squared plus k squared. Both of them will die. So this is bounded by 2. 0 times 2, the result overall is equal to 0. Once we reach this limit, which is, as I told you, it is the corollary of the squeeze theory. Now I have the limit existence equal to 0, so my function is differentiable. The consequence from that my function or our function is differentiable, that I can approximate, or again that I can approximate the value of the function and evaluate the value at 1.1 and 0.9. Which means instead of having 1.1, I can consider it 1 plus 0.1, this is h, and for this guy it's going to be 1 plus minus 0.1, which stands for k. Now I can use the approximation equation as I told you. Of course, that's the approximation that I'm going to have. R is equal to 0. I have the values at a and b, which are here, as you can see from the definition. All I have to do is to just direct substitution. So it's going to be 1 plus 0.1, 1 plus negative 0.1, which is going to be at 1.1 and 0.9. The value of the function at 1 and 1, which is 1, times the partial derivatives times h and k, which will lead to 1.2, as you can see. I sent you the PDF earlier just to go through it. And once more, all the details of our problem evaluation. It's already, I'm discussing it with you. And if you have any question, please stop by in the office hours or in our office at any time for more questions. As you can see, for this test or for this function, this is differentiable. I get the gain of approximating the value of the function at the point 1.1 or 0.9. Wallahi, this is really very tempting for a question in an exam to test the differentiability and to evaluate the value of the function at certain point. Once more, this is to summarize everything. That's the remainder term that I am checking if I want to find the function is differentiable or not. Let's test this problem also. He wants you to show that f of xy is differentiable function at the origin. And as you can see, it's a piecewise function. That's your function. And when it's equal to the origin, the value will equal to 0. So once more, I will test using the 3 steps that we spoke about. So the first of them is to get the partial derivatives. Since my function is given by a piecewise function, I will use the definition in order to evaluate the partial derivatives, as we did previously. All I have to do is to make the substitution. So if you start substituting for f of h and 0, it's gonna be h plus 0. This is gonna be 0, so the denominator is equal to 0, divided by h squared plus 0, which is gonna be h squared. So once you try to put it all together, it will equal to 0. So the limit exists, or the partial derivative exists in the direction of x is equal to 0, and in similar manner for y it's also existent equal to 0. So both partial derivatives exist, both of them are equal to 0 at this stage. The second step is to get the remainder term. How to get the remainder term? It is from the main equation, as I told you previously. So once more, r of xy is equal to the value of the function minus the value of the function at the point that you are going to justify the existence of the partial derivatives, minus the partial derivative at the origin, which is 0. So simply, in my problem, or this problem, the value of f at 0 and 0, it's equal to 0. So this guy is 0. The partial derivative at x equal to the origin, it is already 0. The partial derivative y is equal to 0. So the problem now, it is the limit of x and y approaching the origin. All I have is the value of the function, which is simply x squared sine of y divided by the root of x squared plus y squared, and also it is divided by the norm of this guy, which is x squared plus y squared. That's the value of the function after we substitute. So once more, that's the value of the function exactly as I explained to you. That's the value of the function. So this is the result. Now I will need to find the value of this limit, which is x squared times sine y divided by the root of x squared plus y squared will be multiplied and x squared by y squared. This y squared roots will be cancelled, or I will have them raised. Now I have x squared, I will try to separate it. Separating it will help you to use the squeeze theory. So this is going to be the limit of x and y tends to the origin. So once more, the limit is equal to 0. Now I need to find that this limit is actually bounded. It's very simple to prove, because once more, the limit of x squared over x squared plus y squared, it is less than or equal to x squared plus y squared divided by x squared plus y squared. So it's less than or equal to 1. So this part also is bounded by 1. According to the squeeze theory, 0 times 1 equal to 0. So the limit exists and it is equal to 0. It's really very simple to prove, as I told you. And so once more, it's really very simple to prove the function is bounded. As I told you, sin y is equal to 0. So this function is differentiable at the origin. As I told you, I have tried to solve as much as possible from problems at this part. This is a good point or a good part to have problems on your next midterm or in the improvement test down the road. Inshallah, you are not going to need it. So for here, the following example shows a function that has the partial derivative at the origin, xy by the root of xy, x squared plus y squared, and it's not differential at that point. It's test this. All I have to do is to do the steps exactly the same. So finding the partial derivative at the origin, partial f, partial x, partial f, partial y. And for this function, also it's gonna be really very simple. All I have to do is to substitute once more, or I don't know for how many times now, but I can, of course, find partial f, partial x, okay, which is gonna be the limit when h tends to 0 for the function f of h plus 0 minus f at 0 divided by h. So in my case, it's gonna be the limit of h tends to 0. For the function, I will use this guy. Let's make the substitution, which is gonna be a 0 divided by h squared under square root. Remark that this is also h, so the result will be equal to 0. If I'm trying to get the partial derivative with respect to y, it will be exactly the same, but instead of having h plus 0 and 0, it's gonna be 0 plus k plus 0 or the other direction. And in both cases, this is why you will have your gradient vector equal to 0. Of course, you remember that the gradient vector of f at the origin, it is simply partial f, partial x at the origin, and partial f, partial y at the origin. That's the gradient vector. So since those guys are zeros, then your partial derivative exists and it's equal to 0. Now let's prove that f is differentiable, which means I will go to the second step. The second step is to get out of xy, which is by the definition will equal to the value of the function. So this is going to be 0, those guys are equal to zeros. So it's going to be f of xy, which is x y divided by root of x squared y squared. The roots will be multiplied in each other. So it's going to be xy divided by x squared plus y squared. Once more, it can be approximated using it's just enough to show that this limit doesn't exist. It's very, very simple. If you use y equal to x, as I will use here, trying y equal to x, it's going to be x squared divided by 2 over x squared. So actually the limit existence equal to half. Since it's not equal to 0, the function is not differentiable, of course, as you know. Since the half is not equal to 0, so the limit doesn't exist. Once the limit doesn't exist or not equal to 0, then your function is not differentiable. So once more, although the partial derivatives exist, but your function is not differentiable, as discussed. Now, if I want to get a tangent plan for a differentiable function at certain point, all I have to do is to use the part from the equation. Of course, we have here the remainder, but since it is differentiable, the remainder term is equal to 0, and that's exactly the equation of the tangent to your surface or to your function. It's a direct substitution. For example, we want you to consider the function which is given by x squared y squared minus y ln x, and he asks you to find an equation of the tangent plan to the graph of f at the point 1, 2, and the value of the function. So mainly all I have to do in order to get the tangent plan, try to get partial f, partial x, partial f, partial y for this function, which is gonna be a 2 over x y squared, then minus y over x for differentiating with respect to x. Differentiating with respect to y, it's gonna be 2 over x squared y, then minus of ln x, then start substituting of y and of x and y by the values of 1 and 2 in both of them, and then you will be able to get your partial derivatives. So all I had to do is to make the substitution happen. That's the value of the function. This is the first derivative, as I told you, 2xy squared minus y over x. Making the substitution is going to equal to 6. So this part is equal to 6. Similar partial f partial y, which is going to be exactly like this one. Making the substitution, it will lead to 4. So all I have to do is to replace this part, this guy by 6, that one by 4, and also if 1 and 2 is very, very simple, I will make the substitution in this function, replacing every x by 1 and every y by 2, which is going to be 4. So this guy is equal to 4. A direct substitution into this equation, as I told you, this is going to be the value of the tangent plan. Simplifying it, so it's going to be a negative 6 plus negative h, which is negative 14, plus 4, which means negative 10. So simply z is equal to 6x plus 4y minus 10, as you can see. That's the equation of the tangent plan for this function in details. I believe I have a couple of problems also. I've already prepared them for this part. Also, here he is asking you to determine the tangent plan to the graph, similar manner, x squared y, and for e to the power of x minus 1. And to show it is, since the function is differentiable at the domain, all I have to do is to find the partial derivatives and use the substitution at 1 and 2. Similar debate will lead to, this is the partial derivatives. So if I want to find the partial derivatives, of course, for this function with respect to x, it's going to be partial f partial x, which is going to be 2x and y plus e to the power of x minus 1. It's going to be the same. Partial f partial y, it's going to be exactly, also as I told you, differentiating y is going to equal to 1 times x squared, plus this part is going to be cancelled because it doesn't contain any y. So partial f partial y is going to be x squared. Then I will substitute on both partial derivatives by the value of x equal to 1 and y equal to 2. So this is the partial derivative with respect to x, and that's the partial derivative with respect to y. Substituting, it's equal to 1. I have the partial derivatives, so these two parts already exist. I will replace this one by 5, that one by 1, and define the value of the function at 1 and 2. So start substituting by 1 and 2, that's the value of your function, that's the tangent plan. As I told you, this part is very, very simple. Once you go over the remainder term and the limit existence, you will be able to find the tangent plan and to prove the differentiability, as you can see. In order to find what's called the differentials in R2, it's really very simple. And I will start from, as I told you, that for any function near a certain point, it can be approximated by partial f partial x times x minus a, partial f partial y times y minus b. If I move f a b to the other direction, I will have f of xy minus f of ab, which means that x is for small changes or in the x or increments in the x and y, I can actually, as we did in the approximation, getting the value of f of a plus dx, y plus dy, which is going to be simply f of ab plus partial f, and that's the difference between x minus a, or the x a and b minus, a plus dx minus a, and y plus dy minus y. This is why we multiply the dx and dy in this case. And now I can get, as I told you, the difference between the main function at a and the dx minus f of a and b, which is the value of the differential, which is going to equal to the partial derivatives times dx dy. So bottom line, if you are asked to find the differential of, with first, this is going to be the equation that I'm using, the differential of f at ab. Get the first derivative of x at ab times dx, the first derivative of f with respect to y times dy, and you will be able to get your differential. So if f belongs to such that from R2 into RB, differentiable function at point AB, and this point belongs to the interior of your domain, the differential of f at AB is simply, the differential of f at AB is partial f partial x times dx, partial f partial y times dy, as you can see. The differential of f at AB estimates the change in the function value where we make small changes in either x and y or both of them. So the differential is simply also the value of the function plus dx at a plus dx and b plus dy, an increment from x and y minus f of ab. So either you are using the differential by finding the difference, or using the differential by multiplying the partial derivatives in the increment in dx and the dy. They are both the same as I told you. So for this problem in specific, he is asking you to consider that the temperature T in a certain region depends on the position of the point x and y in the plane. And it is defined by this relation. Okay, using the differential, calculate approximately the change in temperature when we move from the point 1, 2 to point 1.3 and 2.2. This is really very simple. From these two remarks, I will remark that dx is equal to 0.3 and dy is equal to 0.2. So all I have to do, if I want to find the differential of my function at 1.3 and 2.2, the differential at 1.3 and 1.2 for our function, is to get partial f, partial x times dx plus partial f, partial y times dy, which is simply gonna be the dx value I already calculated, which is 0.3, the dy value, which is 0.2. Now for the partial derivatives, differentiate your function. With respect to x, it's gonna be 4 of x plus 3y. Differentiating with respect to y, it's gonna be 3 of an x. And start substituting by the point which is 1 and 2 instead of x and y. Then you will have your differential. As I told you, it's really very simple to have. And also, although this problem is really very simple, but when you ask people about it in exams, usually they forget about how to evaluate the differential. So once more, those are dx and dy. And in order to find the differential at 0.3 and 0.2, all I have to do is to get the partial derivative of f with respect to x at 1 and 2, get the partial derivative of the function at y at 1 and 2, multiply both of them by dx dy correspondingly. Those are the value of the partial derivatives. And all I have to do is to just direct substitution, you will have your differential. So either it's a multiple choice problem, or to choose the right solution, it's going to be very, very simple. As you can see, as the temperature increases approximately, also the value will increase to become 3.6. The differentiability in Rn, okay, if f differentiable function at a point, that's a generalization to the results that we have. So if the partial derivatives already exist, this is going to be the remainder term, but in Rn, whatever, divided by the norm also related to Rn, as we saw previously. If f is differentiable function at A, then f is continuous, same consequence as R2. If all first order partial derivatives of f exist and are continuous at a certain point, okay, then f is differentiable at A. If f and g be differentiable function at A, then the addition, the multiplication by scalar, the multiplication of two functions, or the division are also differentiable at this point. If f is differentiable at A and g is differentiable at f of A, then the composition is differentiable, which means f g as a composite of f of A, as you can see. Here, by the previous theorems and the proposition, we may say that, for example, the function xy, y sine xy, is differentiable. This function is differentiable. Why it is differentiable? Because it's consisting of a multiplication and the addition of differentiable functions, exponential, sine, polynomial functions, so it is differential. The differential definition can also easily extended to functions which more than one. the derivative, so the differential as we studied in R2, which is really very simple, which is the multiplication of the partial derivatives times dx and dy. If I want to generalize this into n dimension, it's gonna be exactly the same as I told you, just a generalization of our law. The differential of the differential function of f can be defined and also can be extended to the second partial, the second order derivative, and in this case, this is gonna be the equation of the differential. So that's the differential for R2, that's the differential d of f at a and b, that's the first derivative, which is gonna be partial f, partial x dx plus partial f, partial y times dy, which also can be extended to higher order. This is the first order, that's the higher order, which is going to be the second order, or the second partial derivative of f with respect to x, but times dx squared. The next derivative, but it's times 2 dx dy, and that's with dy squared. Also, if I went for the differential for higher order than the second, it's gonna be following the exact same trend. And I've also, for higher orders, I've added it for you. That's a simplification of the quadratic or the second order differential. You can write dx dy, this is partial, the second derivative, but I prefer the first, this form on the matrix form, but they are similar to each other. And that's, as I told you, this is the first derivative for the differential, evaluating the differential within the first order. That's the differential for the second order, which is, as you can see, just following the equation. And that's for the third order. This is going to be the equation also. So if you are asking about the differential, those are the three equations that we can use for first, second, or third order. Now, we have another topic to talk about, which is the directional derivative. And this is one of the important topics that we can deal with. In this topic, or how to find the directional derivative, we will see this through the coming slides. But before going further, I want you to know why we are doing this. So this paragraph states that the partial derivatives of a function at a certain point measure the effect on the function when we make infinitesimal change in each component, keeping the other constants. That's exactly what we do when we get the first derivative with respect to x or the first derivative with respect to y. And it is, okay, the directional derivative of the function, but in the direction of the x-axis, which is 1 and 0, or the direction of y-axis, which is partial f, partial y, in the direction of 0 and 1. This is stated here. So once more, the partial derivative of a function at a certain point measure the effect on the function when we make infinitesimal change in each component, keeping the other components equal to 0. This is why once you try to get partial f, partial x, it's like having the directional derivative, but in the direction of the x-axis, which is 1 and 0. For y, or for the partial derivative with respect to y, it's going to be exactly the same, but you are using the vector, the unit vector 0 and 1, as you will see down the road. This introduces the next definition, the definition of derivative at a certain point along a direction of a certain vector. So once more, considering the function f, which is running from Rn into R, and while a belongs to the interior of the domain, and a vector u, which is preferable to be a unit vector, I can get the directional derivative, but not insisting on having the vector as a unit vector. But in this case, it's not going to be easy to compare between various vectors. But if we normalize it, which means the gradient, the magnitude or the norm of the vector is equal to 1, I can compare between the value of the function in various directions. And this is why mainly we are using the unit vector. This is the law that we will use in order to find, okay, the derivative of a function at a certain point in the direction of a specific vector. If you remark, if we use u as 1 with 0, it's going to be exactly the equation of partial derivative in the x direction. If I'm using u as 0 and 1, it's going to be exactly the equation of the partial derivative in the y direction. So in this case, for example, or to make things really very easy for you, I would like to solve this problem and to find the directional derivative of this function, which is x times y plus 1, at this specific point, but in the direction of the vector 1 and 1. In order to do this, I usually like to do steps 1, 2, 3. So I will start by first checking if the vector is a unit vector or not. How to check this? I will simply try to get the magnitude of this vector. The magnitude of 1 and 1 is very, very simple. The magnitude is simply going to be the square root, okay, the magnitude of this vector, as we know, the magnitude of this vector is going to be the square root of 1 to the power of 2, 1 to the power of 2. So actually, that's the magnitude of 1 and 1, which is going to be equal to the root of 2, as you can see. So since this is not equal to positive 1, so the magnitude is not, the vector is not on a unit vector. In order to normalize it, all I have to do is to divide the components of this vector on the magnitude. So it's going to be 1 over root 2 and 1 over root 2. This is how to normalize your unit vector. So that's the first step. Okay, v doesn't have norm equal to 1. We must divide v by its norm. So now I have a unit vector which is 1 over root 2 plus 1 over root 2. I will write the law. Law states that the value of the function at the point that you are discussing, which is 1 and 0, plus t at the norm that you are at the unit vector that you are using. So it's a plus t, 1 over root 2 and 1 over 2, minus the value of the function at 1 and 0, and taking the limit while t is equal to 0. Okay, it's going to be 1 plus t over root 2, that's the first component, then 0 plus t over root 2, that's the second component. I will take these two components and substitute in the main function. So all I have to do, the next step, is to take these components and to replace them in x and y position, and this is exactly what happened. Replacing x by 1 plus t over root 2, replacing y by t over root 2, okay? Replacing y, I'm sorry, by t over root 2, so it's going to be 2 over root 2 plus 1. Don't forget, minus the value of the function at 1 and 0. If you make a substitution on 1 and 0, then this is going to be 1 plus 1 times 1, so the value is equal to 1. So I need to find the limit of this function. Just multiplying the brackets and simplifying, eliminating negative 1 with positive 1, taking t as a common, you will have 2 over root 2 plus 2 over root 2. So simplifying, that's the case. Taking the limit, so this part is cancelled. So the the directed derivative of the function at the point 1 and 0 in the direction of the vector 1 and 1 is going to equal to root 2. It's a direct substitution. Once more for the southern time, if you look, just look to the steps and you didn't use your hand in solving these problems, it will look to you, number one, similar to each other. Number two, it will look to you as a complicated steps. But if you solve them using your pen and you're trying to solve as much problems as possible, you will see that it's all similar to each other. Also, I want you to know that instead of using this law in order to get the directional derivative of the function at certain point, I can also use this relation, okay, which is very, very simple compared to that one. All I have to do is to get the gradient of the function at this point times the unit vector that you are discussing, and you will have the exact same result. But you can't use this law unless you are sure about your function that it is differential. I can resolve this problem using this law, since x times y plus 1 is a differential function. So once more, if I want to resolve this problem, if I want to solve this problem using this law, it's really very simple. As you can see, since the function is differentiable, this function is differential because it's a combination of polynomials multiplied in each other. So all I have to do is to get the gradient vector of f, which is really very simple to have. The gradient vector of f will be the derivative of the function with respect to x, which is y plus 1. The derivative of the function with respect to y, which is going to be x. I will get the value of f at the point of discussion, which is 1 and 0. So all I have to do is to make a substitution. This is going to be 1, and please be careful about the substitution. This is going to be 1 and 1. That's the gradient vector. Already have it. The second step is to get u as a normal vector. This is the given vector in order to be normal. So getting v as a normal vector, it's going to be 1 divided by the square root of the sum of the components. So it's going to be 1 over root 2 and 1 over root 2, as you can see. Now all I have to do is to multiply these two guys by this law. So the differential of the function at the point 1 and 0 in the direction of the vector 1 and 1 simply will be 1 and 1 times 1 over root 2 and 1 over root 2, which is simply going to be 2 over root 2, exactly like the result that we have in the previous slide. So as I told you, the steps are really very simple to use. So as you saw, this problem, we already solved it twice. We solved it using the definition, and also we take advantage of solving the problem